Oh, right. So this is D9, not C9. Okay, but you sure you use a pencil for this? You sure you use a pencil for this? No, it's D9. Show you later. Does anyone else not have a packet? I think everyone's gotten theirs now. All right. So what we're going to talk about for D9 and D10 is we're going to continue our discussion of molecular covalent. And in D9 and D10, we're really talking about what makes the molecules shape the way that they're shaped, okay? And you've heard me mention a lot when we're drawing our dot structures, get the electron pairs as far apart as possible. That idea of electron pairs repelling each other is really what it's what determines the shape of molecules, okay? So, the theory that kind of underlies molecular shape is called VSEPR theory, okay? I know that doesn't exactly say VSEPR, but scientists just call it VSEPR, okay? VSEPR stands for valence shell electron pair repulsion. Valence shell electron pair repulsion. Okay, so that's this idea that electron pairs repel each other. So if you have a bonded pair over here and a bonded pair up here, this one's going to swing around to get as far apart as possible from the other bonded pair, okay? So for number 2, I want you to fill in the formulas for each of these substances, okay? And then tell me whether they're ionic, molecular, covalent, or metallic, okay? So you memorize the formula for all these in Unit A. If you don't remember, you can look back at your green sheet. But you memorize the formula for all of these in Unit A. Don't remember?
I know water.
You know water. Okay, good.
Bold assumption.
I know water. Oh, ammonia. Carbon dioxide too.
Ammonia is not ammonium. Those are two different things.
Yeah. Oh, I'm like definitely supposed to know these.
Yes.
Definitely didn't do that. You live and you learn.
Look here where it says common compounds. You memorize these back in Unit A.
Anyone actually memorize?
Yeah, they
I
did.
got the question right on the tab.
Yeah, I like water and carbon dioxide. I know those are the parts.
Nothing else.
Oh, yeah.
The one
we
I
were
don't know was a
looking-
million. Okay, let's do it.
Okay, so, and then for number 2, write down, circle whether these are all ionic, are they all molecular covalent, or are they all metallic? Okay, so water, as we know, is H2O. Ammonia is NH3. It's not ammonium, it's ammonia. Methane is CH4. Carbon dioxide, as you know, is CO2. Formaldehyde, we never learned. I'm just telling you it's CH2O. Okay? So, what are all these? Ionic, molecular, covalent, or metallic? Molecular covalent. They are all nonmetals bonded together. Okay? So these are some of the quintessential kind of standard, simple molecules that exist in the world. Okay? All right, now we're going to use a pencil, please, in case you mess up your dot diagram. I want you to draw the Lewis dot diagram, and then I want you to draw the structural formula for each one. Okay? The structural formula is when you change the bonds into lines. Okay? For these last two, you definitely need to use method 2. Like we did in the do now, where you add up all the electrons on the side. For these ones, you can use method 1 or method 2. Okay, these ones are pretty easy to picture how they're going to fit together. Okay? They're covalent. Is there going to be arrows?
No.
No. Last period, everyone drew arrows. I don't know why.
That's fine.
These are covalent. There's not going to be any arrows. They're going to be sharing electrons. Okay? They're going to be sharing electrons. So for number 1, I know that O is the central atom. And I'm just going to give it its valence electrons because I can picture where the H's are going to latch on, right? That's how we do method 1, where you just jigsaw it together. Okay, you could do method 2 if you wanted, but. So try that same thing for ammonia and methane. Draw the central atom first with its valence electrons, and then latch on the hydrogens. Let me know if you get stuck on any of them. So this one you got to do left one. It's too hard to get it to fix that again. Keep the one. Yeah, the dots like above and below those. So for the last two, use method 2, okay? Just add up all the electrons on the side, because it's going to be hard. Yeah, add them up on the side, because that method 1's not going to work. Yeah, add them up again. It will be eventually. Yeah. Literally, the carbon doesn't have a full octet anymore.
Oh.
Yeah. Make some double bonds. So for the last two, you will need some double bonds to get it to work. So for the last one, the skeleton structure, C will be in the middle, and then you can do an H on either side, and then an O. I don't care which side has which, but just be sure C is in the middle, okay? Okay, once you've got your dot structures, then draw your line structures, okay? So, you know, your structural formulas look like that, but keep your lone pairs, but the bonding pairs turn into lines. Okay, so let's go over these. Also, if you're still confused about method 1, which would be a good method to use for these, and method 2, which would be a good method to draw these, listen up, okay? If you're still confused by those two methods. Method 1 means you jigsaw it together, okay? You put the electrons on the central atom, and then you can immediately see where the other ones fit. Method 1 works well for very simple molecules, okay? I can picture N with its 5 valence electrons. I can see where the 3 H's are going to go. That's method 1. You just jigsaw it together, okay? This is a good candidate for method 1 because I can picture the carbon with 4 valence electrons and I can see where the 4 hydrogens are going to latch on, okay? Like that, okay? And remember, the hydrogens are full with just 2. So all these hydrogens are full, the central atoms have a full octet, we're good, okay? Carbon dioxide, do not put 4 on the carbon. Don't do like we did with method 1. Don't put 4 dots around the carbon. Because you can tell it's not going to work. If this has 4, this has 6, and this has 6, there's no way for it to easily fit together. When you do method 2, don't draw the dots, just add them up on the side. Carbon has 4, oxygen has 6, oxygen has 6. So we have a total of 16. Okay, make your single bonds first. Notice I'm not interested in which ones were the carbons and which ones were the oxygens originally. I'm just placing these where they need to be. Then you fill the outer atoms next. Fill the octets of the outer atoms next. And I think that's 16. Okay, if I had more, I'd put them on the carbon, but I don't have any more. So what I need to do is make some double bonds. So take some off of this, move them to the middle. Take some off of this, move them to the middle. I had been drawing an X and showing them move. You don't have to do that, okay? I just did that for your notes so you would know where they came from. But now that you know where they're coming from, feel free to just erase them and move them, okay? And by sharing more, now the carbon in the middle has a full octet, okay? But we would have never figured this out with the method 1, okay? If you can't figure it out with method 1, just put all the electrons in a big pot and then distribute them where they need to be, okay? Same thing with this one, okay? It's too hard to picture how it would work. So just add up the electrons on the side. So 4 plus 6 plus 1 plus 1, that's 12, okay? Make single bonds first. Okay, so you'll know that everything needs at least a single bond, so that's why we do that first. What do we fill next, outer or central? Outer, okay? Here's the mistake a lot of people make. Is this correct? No, hydrogen is full with 2. Never put more than 2 around hydrogen. As soon as you see a hydrogen with a 2, it's good. This hydrogen's good, this hydrogen's good. It's the oxygen you should focus on. So that's 2, 4, 6, 8, 10, 12. Okay, if we had more, we would put them on the carbon, but we don't have any more. So what are we going to have to do? Make a double bond. So take some off the oxygen and move them to the middle. Don't give them to the carbon, share them with the carbon. So the oxygen still has them, but now the carbon has them too. Okay? All right, so now let's draw what this would look like as a structural formula. So you would have the carbon in the middle, and it would be a double bond to the oxygen. Okay? And these electron pairs repel each other. They're going to swing out to the corners. Corner, corner, like that. So they can be a full 120 degrees away from each other. That space won't stay empty. Same thing's going to happen up here. There's all this empty space up here. These bonded pairs are also going to swing to the corners. So it'll look more like that. Okay, so that all these bonding pairs and unbonded pairs want to get absolutely as far apart as possible. That's what VSEPR theory is. Okay. This one, it'll just be carbon, double bond, oxygen, and the lone pairs are going to swing out onto the corners as well. The lone pairs on the oxygen. Okay, like that. The methane is very simple. Single bond H, single bond H, single bond H, single bond H. Nitrogen will be single bond H, single bond H, single bond H, and keep that lone pair. Okay, so you should still draw the lone pairs, but the bonded pairs become lines. But keep your lone pairs as dots. Okay. So if I ask for the Lewis structure, it's what's in the first column. If I ask for the structural formula, that's what's in the second column. Okay, so now we're going to talk about how these look in 3 dimensions. Okay, how do these look in 3 dimensions? So we're going to start actually with method. Let's do this. Okay, let's start with methane because that's the most simple atom. How many satellite atoms are around the central atom? So that just means how many atoms are around the central atom? There are 4. Okay. And the second question says how many lone pairs are around the central atom? There are 0. There's no lone pairs on the central atom. Okay, so what does it look like this angle is right here? If this was math class, what would you say that angle is? It looks like 90 degrees, right? So it appears when we draw these molecules on paper, it appears that they look like this, right? 90 degrees. But are these molecules flat? No. Could these bonded pairs get further apart in 3 dimensions? Do you think I can get them further apart than 90 degrees? Yes. So if you do it like this, look what I just did there. Okay, so the shape that I made, notice how all the bond angles are slightly obtuse? Is that the right word? Obtuse?
Yeah.
Greater than 90? All the bond angles now are slightly greater than 90. By breaking it out into 3 dimensions, look at this shape right here, okay? By breaking it out into 3 dimensions, I got all the bonded pairs a little further apart than 90 degrees, okay? So when we draw it flat like that, what you got to picture is this, okay? And the word for this shape is a tetrahedron, okay? So, and the angle, if you were to hold a protractor up to it, the bond angle for all of these is 109.5 degrees, okay? So they're able, in 3 dimensions, to get a little further apart than 90 degrees. And the name for the shape is tetrahedral. And tetrahedron is kind of the quintessential chemistry shape, okay? Because the most bonds something can have is 4 bonds. So if it has 4 single bonds, the shape that it takes is tetrahedral, okay? I know when we draw it, it looks kind of like this. You can see how it appears to be 90 degrees from a certain perspective, okay? But you've got to remember, when you see it and it looks like 90 degrees, it's actually a tetrahedron. It's actually 109.5, okay? Ammonia, okay. There are 3 atoms around the central atom. And I want you to put a little balloon around the lone pair. There's 1 lone pair on the central atom. That lone pair takes up a lot more space than you might think, okay? So you think, oh, it's just a tiny lone pair. It's not taking up that much space. I got a special toothpick just for a lone pair. Okay, so this is the toothpick. Have you ever used those toothpicks? They're a little like curly on the end. So what I have, the nitrogen's in the middle. Yeah, they're kind of fancy. So we have the nitrogen in the middle, and then single bond H, single bond H, single bond H, and then the lone pair coming off the top, okay? So even though it looks like a 90-degree situation here, in 3 dimensions it looks like this, okay? The nitrogen's here, and then those 3 hydrogens are down there, and this is a lone pair, okay? The lone pair is moving around a lot more than you would think. The lone pair actually takes up more space than a bonded pair, okay? Put little arrows on either side of this lone pair. Because the lone pair is not stuck in a bond, it's moving a lot. And because this lone pair is moving a lot, it actually pushes these a little closer together than they would normally be. So in a tetrahedron, they were 109.5. In this structure, they're only 107. Okay, so everything gets pushed a little closer together because of that lone pair is kind of going a little wild. Okay, it's moving a lot more than you would think. And the name of this shape, if you look at it and you kind of ignore the lone pair, it kind of looks like a little pyramid. Okay, it's like a little pyramid. So it's called trigonal pyramidal because it's a pyramid that has a triangle at the base. So trigonal pyramidal. Is that how you would normally pronounce that word? If you saw that word, what would you think it is?
I thought it was an
A lot of people say trigonal pyramidal,
I
right?
would say like pyramidal.
Pyramidal, yeah.
Pyramidal.
My high school chemistry teacher said pyramidal. And then I got to college and everyone's like, what?
Wait, how did you say it?
Pyramidal. Say it after me, pyramidal.
Pyramidal.
I want you to sound smart when you get to college. And if you say pyramidal, they'll know that you know what you're talking
They'll
about.
know I'm really smart.
Yeah. Because everyone that's never heard of it says pyramidal. But everyone that's learned it says pyramidal.
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 Yeah, I'm definitely gonna get about 2 hours into that and then go.
All right.
I still said silicone when you try, it's still a silicone when you try to tell us.
And so silicon.
Yeah. Literally a day after.
That one has an E on the end. All right. How many satellite atoms are here? 2. How many lone pairs? 2. So it's going to look, okay, it's going to look like this. All right. So we have the oxygen, the 2 hydrogens, and we got these 2 lone pairs coming off. The 2 lone pairs are taking up even more space, and they're pushing these even closer together. So the bond angle is going to get even a little tighter. It's going to be 104.5. Sounds like a radio station. Okay. And the word for this shape, if you kind of ignore the lone pairs, the lone pairs are taking up space and they affect the shape, but they're not really a part of the shape. Just look at this shape right here. We call this bent. Okay, we call this bent.
That's the most simple chemistry term I've ever heard in my life.
Bent. Haven't you heard in biology water is bent?
No.
Water's bent. The water molecule is bent.
No, we did Zoom biology.
Okay.
I'm in AP bio, I still never heard that.
So that's why water molecules are bent and they're not in a straight line, is because they have those 2 lone pairs there. And then water being bent is what causes water to be polar. So you probably heard that water's polar in
Yeah,
biology.
no, I've heard that.
The reason water's polar is because it's bent, and the reason it's bent is because it has those 2 lone pairs.
Wait.
All of science makes sense.
We'll learn more later why bent means it's polar. But okay.
It's polar because it's bent, you said?
Yeah, having an asymmetrical shape creates polarity.
Okay, gotcha.
It's more complicated than that. We'll learn more later. All right. This carbon dioxide. How many satellite atoms, everyone? 2. How many lone pairs are on the central atom? 0. Okay. Only look at the central atom in terms of what affects the shape. So when you don't have any lone pairs, it's not going to be bent. Okay. When you don't have any lone pairs taking up space, these can get a full 180 degrees apart. Okay. So those will be 180 degrees linear. Okay, so carbon dioxide is a linear molecule, whereas water is a bent molecule. Okay, and carbon dioxide being linear means it's nonpolar, and nonpolar is what leads to carbon dioxide being a gas. Being polar is what leads to water being a liquid. And then the last one, how many satellite atoms, everyone?
3.
And how many lone pairs are on the central atom? 0. Okay. So the way that 3 things get as far apart as they can, they actually don't need to go into 3 dimensions. Like when I saw this and saw that it would stay flat, I thought there would surely be a way for them to get further apart in 3 dimensions. But this is as far apart as they can get, 120 degrees. Okay. So when you have 3 things around the central atom, they'll be 120 degrees apart. And this is not called trigonal pyramidal, it's called trigonal planar because it's in a flat plane. Trigonal planar is flat, okay? Trigonal pyramidal is if you stick a lone pair up here and then it pushes these down, okay, into a pyramid shape. All right, so that is it for D9.